Picture 2 quadrillion suns. Not 1,000, not 1,000,000, not 1,000,000,000. 2 quadrillion. A number so vast it doesn't live in human language. It only exists in mathematics and nightmares. This is the Phoenix Cluster, a structure 6 million light-years across, blazing in X-ray frequencies so intense that if your eyes could see it, the light would sear through you before you had time to blink. And somewhere inside that inferno, at its absolute center, something is breaking the rules. Not bending them, not pushing at their edges, breaking them. Completely, irreversibly. And every cosmological model we have built in a century of science cannot explain it. Meet Phoenix A, 100 billion times the mass of our sun. Let that land for a moment. Our own black hole, Sagittarius A star at the center of the Milky Way, is a mere 4 million solar masses. TON 618, the largest black hole most of you have probably heard of, tips the scales at 66 billion. We used to think that was incomprehensible. Phoenix A is 50% more massive than TON 618. And here is the part that should make every physicist in the world deeply uncomfortable. According to everything we know about how the universe works, this object should not exist. It is not merely the largest, it is the wrong size, for the wrong universe, at the wrong time. And we are only beginning to understand why. Let's talk about size. Because statistics alone won't do this justice. You need to feel it. The event horizon of Phoenix A, the point of no return, the edge of the abyss, spans approximately 590 billion kilometers across. Our entire solar system, from the Sun to Neptune, is about 9 billion kilometers wide. So if Phoenix A were placed where our Sun is right now, it wouldn't just consume the planets. Mercury? Gone. Venus? Gone. Earth? Gone. Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all gone. But we wouldn't even be close to the event horizon yet. The heliosphere, the vast magnetic bubble that Pluto sits inside, the boundary that defines where our sun's influence ends, that would be swallowed whole. And still we'd be inside the black hole. Voyager 1 launched in 1977. It has been traveling at 38,000 miles per hour for nearly 50 years. Right now, it is the most distant human-made object in existence, just barely crossing the heliopause. If Voyager 1 were heading toward the center of Phoenix A, it would still be closer to the edge than to the middle. Think about that. 50 years of travel, and you haven't even crossed the halfway point of the darkness. Here is something deeply counterintuitive and deeply terrifying. Small black holes are violent killers. If you fell toward a stellar mass black hole, the kind formed by a dying star, the tidal forces would stretch you like taffy before you even crossed the event horizon. Your feet, being closer to the singularity, would experience gravity billions of times stronger than your head. You would be spaghettified, pulled apart at the molecular level in a fraction of a second. It would be the most violent death the universe offers. But Phoenix A is different. Because it is so massive, its event horizon is so far from the singularity at its core that the tidal forces at the boundary are almost nothing, almost gentle. If you were drifting, weightless, peaceful, eyes open, toward the event horizon of Phoenix A, you would feel nothing change. No alarm, no shudder, no sensation of crossing a threshold. You would simply drift, and drift, and drift. And then, slowly, you would notice the stars behind you beginning to move, bending, warping inward. As space-time itself curves around you, every photon of light from the universe behind you is being compressed, dragged, pulled, until the entire observable universe condenses into a single, shrinking needle of light. A bright point, directly behind you, growing smaller. And in that moment, you would understand. You are already inside, There is no going back. There has not been for a very long time. Now, let's talk about cheating. The universe has rules, and one of the most fundamental rules governing black holes is something called the Eddington limit. Named after the astronomer Arthur Eddington, it describes the maximum rate at which a black hole can consume matter. Here is the problem. As a black hole eats, the infalling matter heats up and radiates. It releases enormous amounts of energy as light and radiation. And that radiation pushes back against the incoming gas, like trying to drink through a straw while someone blows through it from the other direction. At a certain point, the Eddington limit, the outward radiation pressure perfectly balances the inward gravitational pull. The black hole can eat no faster without blowing its own food away. Now do the math with Phoenix A. The universe is 13.8 billion years old. The first stars didn't form until a few 100 million years in. And yet, somehow, Phoenix A has accumulated 100 billion solar masses. If it grew at the absolute maximum rate, at the Eddington limit, without pause, without interruption, starting from the very first possible moment, the numbers still don't work. It's too big. It's too old. It cheated. Somehow it cheated the math. So how? How does a black hole become this large in a universe that simply hasn't been alive long enough? Two theories. Both are extraordinary. Both might be true. Theory 1. Direct collapse black holes. In the very early universe, a cosmos less than 1 billion years old, flooded with hydrogen and helium, there were no heavy elements. No carbon, no iron, no molecular clouds complex enough to fragment into stars. Under certain conditions, enormous clouds of primordial gas, millions of solar masses, could collapse directly. Not into a star, straight into a black hole. Skipping the stellar phase entirely. These are called direct collapse black holes, DCBHs. Born massive, already ahead of the curve. Already with a head start of 100,000 solar masses before they'd eaten a single star. Theory 2. Stupendously large black holes, born at the Big Bang itself. Primordial black holes. The theory goes that quantum fluctuations in the first fractions of a second of the universe, when everything was unimaginably dense, could have directly produced black holes of enormous mass. Not from collapsing stars, not from merging galaxies, from the raw chaos of creation itself. If a primordial black hole of sufficient mass formed in those first milliseconds, it would have had the entire age of the universe to feed. 13.8 billion years, an eternity of eating. We don't know which is true. We don't even know if either is true. But Phoenix A demands an explanation, because the standard model of cosmic evolution simply cannot produce it. In most galaxy clusters, including our own local group, there is a system, a balance, a cosmic thermostat. Here is how it works. Hot gas in the cluster slowly cools. As it cools, it falls toward the center, toward the black hole. The black hole feeds, and as it feeds, it launches jets, enormous plasma jets moving at near light speed, stabbing outward through the cluster, depositing enormous amounts of energy into the gas. The gas heats up. It stops cooling. It stops falling. The black hole stops feeding. Balance. Equilibrium. This feedback loop is one of the most elegant systems in the cosmos. It regulates galaxy growth. It controls star formation. It determines the fate of entire clusters spanning millions of light years. In Phoenix, this system has completely failed. The cooling is happening at a rate that the jets simply cannot keep up with. Gas is flowing inward at an astonishing pace. Roughly 1,000 solar masses per year are pouring into the cluster core. The thermostat is broken. The feedback loop has collapsed. And the result is something we have never seen anywhere else in the observable universe. Our Milky Way, our ancient 400 billion star home, forms between 1 and 2 new stars per year. At that rate, it would take 1 million years to build a modest star cluster. The Phoenix cluster is forming 1,000 stars per year, 500 times our rate. The galaxy at the center of the Phoenix cluster is not aging, it is exploding with youth. Entire stellar nurseries blazing into existence simultaneously, filling the galaxy with hot blue supergiants, the brightest, most energetic stars in the universe, each burning 1,000,000 times brighter than our sun, each living only a few million years before detonating. Imagine looking up from a planet in that galaxy. Every direction, the sky ablaze with brilliant blue fire. Stars so close and so bright that space itself glows between them. The whole galaxy humming with the violent energy of creation at industrial scale. And beneath all of it, pulling, feeding, growing, the dark engine. Phoenix A, silent, patient, consuming everything the chaos produces. Here is the most unsettling thing about Phoenix A. We only found it because it is eating. An active black hole is messy. Gas and dust heat up as they spiral inward, radiating enormous energy across the electromagnetic spectrum. X-rays, radio waves, optical light. It announces itself. It cannot hide when it is feeding. But what happens when it finishes? What happens when Phoenix A, billions of years from now, has consumed the last available gas, has quieted its jets, has grown still and cold and dark? It becomes invisible. A quiescent black hole of this mass emits nothing detectable at cosmological distances. No jets, no accretion disk, no X-ray glow. Just a gravity well, an absence, hidden inside the dead husk of a galaxy, in the cold dark between clusters that have long since dissipated. And here's the question that should keep you awake tonight. How many are there? How many black holes of 100 billion solar masses, or more, are sitting in perfect silence, in the voids between galaxies, completely invisible to every instrument we have ever built or imagined? The honest answer is, we have no idea. Not even a good estimate. They could be rare. They could be everywhere. We simply cannot see them. Let's talk about time. Real time. Incomprehensible time. In roughly 1 trillion years, a number 100 times larger than the current age of the universe, the last red dwarf stars will flicker out. The era of stars will be over. The universe will be dark. Phoenix A will still exist. In roughly 10 to the 32nd years, 10 followed by 32 zeros, the last protons in ordinary matter will decay. Atoms themselves will cease to exist. The universe will be an expanding sea of electrons, positrons, and photons. Phoenix A will still exist. Hawking radiation, the theoretical quantum evaporation of black holes first predicted by Stephen Hawking, will have been slowly, agonizingly bleeding Phoenix A of mass for all of this time. But for a black hole of this mass, the evaporation timescale is approximately 10 to the 100th power years. 10 to the 100th power, a Google of years. Every star in every galaxy, dead. Every planet, disintegrated. Every proton, decayed. Every black hole smaller than Phoenix A, evaporated. And Phoenix A is still there, holding the darkness, ruling over a kingdom of absolute nothing, alone. One final thought. The light we see from the Phoenix cluster today, the X-rays captured by our telescopes, the data that revealed this monster to us, that light left its source 5.7 billion years ago. 5.7 billion years ago. Our solar system did not exist. The sun had not yet ignited. The Earth was not a planet. It was scattered dust and debris drifting in an unnamed region of an unremarkable galaxy. There was no ocean, no land, no life, no concept of life. And yet, in that moment, 5.7 billion years ago, Phoenix A was doing exactly what we are seeing now. Feeding, forming stars, breaking the laws of physics with its impossible size. The entire history of life on Earth, every organism, every ecosystem, every mass extinction, every evolutionary leap, every human civilization, every war, every discovery, every moment that has ever mattered to our species, all of it occurred while that single feeding event was traveling toward us. We are watching the past, and the past is watching us right back. Phoenix A is the largest thing we have ever confirmed to exist. It is older than our world, more massive than our imagination was built to handle, and it is almost certainly not the largest thing that exists. Somewhere in the dark, in the vast, cold, silent voids that light has not yet crossed, there may be things larger still. Things that eat galaxies the way our black hole eats gas clouds. Things born in the first millisecond of creation that have had the entirety of cosmic time to grow. We cannot see them. We cannot detect them. We can only suspect. Which brings me to you. If the universe hides monsters this large in the dark, what do you think is the true upper limit of what space-time can create? Leave your answer below. I will be reading every single one.